In this problem, we are given a circuit diagram that looks like this. For this current, we need to use the node voltage method to find V1, V2, and I1. I provided an example of what a basic node voltage method would look like, as well as the steps and equations for this example right here. It's also linked below in the notes. To start this problem, I'm going to define both of our nodes. That's going to be the same. So our node 1 is going to be right here, and then our node 2 will be right here. And our node 2 is going to look like this. It's going to be a plus minus, and it is going from positive to the negative. Same thing for our voltage 1. It is going like this. And our I1 is in the middle right here. We'll have to solve for that later. So first, I am going to do our node 1 equation. Normally we have V1 minus our voltage source, and this is going to be divided by our first resistor. When we look at this though, we're not given an initial voltage. We don't know V1 either, but if we look at this, we can see that this resistor and this resistor are in parallel. And since both of these resistors are in parallel, that means the voltage across them is the same. So we don't need to calculate for the source voltage. However, the resistance is different, and this is going to matter because we're looking at current. We know the current formula to be a different way of writing the voltage formula, and we can rewrite this as voltage over resistance is equal to current, and current is not the same through parallel. So we are going to have our V1 over the first resistor, which is 60 ohms. After this, we have a V1 over our R1. We don't know our V1 still, so we just have V1, and our R1 is 15 ohms. From here, we have a plus, and then V1 minus our V2, and this is going to be divided by our second resistor, and this is 5 ohms. And now we would set this equal. So we set this equal. Normally, the currents going into a node are equal to 0. That's what it says right here, and that it holds true for this. The currents going into here is equal to 0. However, for our current, we know that this is not the case. We are given that our current is going like this and into here. It's going to split through here and through here because it is in parallel. However, when we are coming out of it, this all has to equal 15. All of the currents in here will have to eventually equal 15 because that is the max amps being pushed in. So this is equal to 15. Also, the reason why this is positive is because the voltage for 1 is going down right here or out of the node, and going out of the node is positive, going into the node is negative. Same thing for V1 over 15. And then for V1 minus V2, the reason why it's V1 minus V2 is because these circuits right here are in series, and since they're in series, the voltage is different. So we are going to take the voltage that we have at V1, we are going to subtract it from this over the 5 ohm resistor because some voltage is lost when we go like this. Next, we are going to make our second equation. Our second equation is starting with V2 minus V1, and it's going out from this node right here. It's the same reason why we did this, except it'll be basically going this way out of our node. And this is over the 5 ohm resistor again. After this, we have a plus V2 over R2 because we have to look at this part. So we have a V2 over 2 ohms. And then after we do this, we have to subtract the current going through. However, we're still not subtracting. This is another difference between our example problem and our given equation. So in here, it says to subtract the current. That's because the current is going into the node like this. However, for our problem, we can see that our current is actually going away from our node. So that means we're going to have a plus 5 amps, and that is equal to 0. Now we can start simplifying things. So for this first equation, I'm going to multiply everything by 60, and then for our second equation, I'm going to multiply everything by 10 and combine like terms. Now that we have both of our equations, we can solve for either V2 or V1. I'm just going to solve for V2. It doesn't really matter. I'm going to look at this equation right here. If I solve for V2, I'll get this, and then I'm going to plug it into our first equation. Plug it into our first equation, I get this, and now I'm going to combine like terms. I also totally forgot about the units. This should be amps times ohms, and this will be a voltage right here. So that means this is going to be 50 volts, and this will also be 900 volts. So now we're going to multiply everything by 7 and then combine like terms. After we do all this, we're going to get that our V1 is equal to 60 volts. So this is the answer for V1. Now we need to solve for V2. We can plug it back into either of these. I'm just going to, for simplicity, plug it back into this equation. When we do this, we are going to get that we have a 7V2 minus 120 equal to a negative 50 volts, and this 120 should also be in volts. we do this, we're going to see we have a 7v2 is equal to 70. And that means our v2 is equal to 10. Lastly, we want to find I1. I1 is slightly different from our v1. It's not actually in this column right here, it's right next to it right here. So to find this, we need to use the I0 formula. And this formula is found in a different set of instructions, and this is for the node voltage method with dependent sources. These are the instructions right here, and then we are going to use this I0 to solve for it since it's right in the middle. So we will have our I0 is equal to our voltage 1 minus our voltage 2, and this is divided by the resistance between them. So we have our I0 is equal to the voltage we found, which is 60, minus the other voltage we found, which is 10, divided by 5 ohms, and we should have voltage up here. Voltage divided by ohms is amps, so we know that's correct, and then we are going to have a 50 divided by 5, so 10. That means our I0 is equal to 10 amps, and this is the solution for this problem.